Hi, I'm Sinivas from NREL. I want to thank you for the opportunity to present at this event. I recently saw a NOAA documentary on PBS, We Can Cool the Planet. I found it quite enlightening. We apparently burn about 10 gigatons of fossil fuel every year. That is a lot, and it does really blow my mind. Here's an interesting fact. Since the Industrial Revolution, we have infused about 1,000 gigatons of CO2 into the atmosphere. And in return, it affects the climate. This burning of fossil fuel emits 37 gigatons of CO2 into the atmosphere yearly. Yikes. This causes temperatures and sea level to rise, greater pollution, more hunger and famine, stronger viruses, more disease and deaths. In our current COVID-19 pandemic, we have lost more than 250,000 lives. And it's only going to get worse if we don't do anything about it. So the big question is, are we too late to reverse or slow the process down? Granted, there are technologies being developed to reverse the process, improve efficiency, and waste management. But our focus should be to reducing the current CO2 emissions to slow the process down. So, how do we do that? Simple, really. We must transition off fossil fuels into renewable resources. I am here today to pitch one small piece of this big puzzle involving wind resource. An innovative offshore floating wind system called SpiderFLOAT. Before I talk about the details of SpiderFLOAT, let me quickly address why floating offshore wind. To reach 35% of US electric generation from wind by 2050, we need to exploit offshore resources. This reference is per DOE 2015 Wind Vision Study. 58% of the resource in waters deeper than 60 meters require a floating system. So, the total available market, TAM, for floating offshore wind is about 50 gigawatts, and it's worth about $40 billion. This leads to the question, why have we not seen floating offshore wind penetrate the US market? Well, the problem is economics. We need to make it somewhat competitive to other energy resources. The current floating substructure design, not including the tower or turbine, are derivatives of the oil and gas industry, which are traditionally designed as one-off steel structures, resulting in bulky and expensive designs. Current estimates are about $1 million per megawatt per substructure. Now, this does not include the tower or the turbine. So, typically a 10 megawatt system, the substructure cost will be about $10 million. The LCOE using oil and gas technology is about 18 cents a kilowatt hour, and we really need to get it to less than 7.5 cents a kilowatt hour to be competitive. So, how do we get there? Well, we can get there with the SpiderFLOAT to less than 7.5 cents a kilowatt hour. Important thing to point out here is the simplicity of the system. First, by using moment-free connection with universal joint 7 that allows flexibility of the fiberglass cans 6 and arms 4, we essentially reduce the loads being transmitted from the waves to the central column and to the turbine, making the system more stable to capture more energy from the wind. In addition to making it lightweight too. The flexibility is controlled by the actuators too. Second, note that the material is placed strategically. Lighter stuff closer to the top, fiberglass cans 6, and heavy stuff at the bottom, arms 4. You want the heavy stuff on the bottom. It's like the keel on a boat. This gives stability to the system. Third, modularity allows for the system of various parts to be built in factories, on-site manufacturing, and assembled at port for quayside pre-commissioning, reducing offshore operations and cost. Compared to a substructure based on oil and gas design, the SpiderFLOAT offers a modular design with structural compliance for lightweight substructure. This allows for 20% cost reduction in CapEx, leveraging local supply chain and on-site manufacturing. we can get there with SpiderFLOAT to less than 7.5 cents a kilowatt hour. Let's look at the cost reduction of a few competitors in the market, mostly from Europe. We are comparing here to Guycon, EDO, Aerodyne, X1 Wind, and Tetraspark. Looking at this table, SpiderFLOAT modular design provides the biggest cost reduction compared to the others, with some reduction in material cost too. As mentioned before, the SpiderFLOAT value proposition is a total of 20% cost reduction of the substructure CapEx. So let's look at the target market, and let's only look at the United States. The total available market, as previously mentioned, is about 40 billion. The serviceable available market, SAM, is about 50% of TAM at 20 billion. And the serviceable obtainable market, SOM, for the SpiderFLOAT technology is about 10 billion. This amount identified is for the US market only, and the world market would be larger. Potential customers in California could be Equinor, Trident Wind, Redwood Coast Energy Authority, or potential future BOEM lease awardees in California. Here is our business model canvas of the startup. Revenue will be generated via royalties, consulting, and providing engineering services for the SpiderFLOAT. The SpiderFLOAT started with a laboratory-directed research and development (LDRD) funds, and it currently has continued funding for a wave basin model test through a technology commercialization fund (TCF) of $400,000 and an ARPA-E Atlantis control co-design effort of $1.5 million. To continue to de-risk the technology, we will be applying for phase 2 of the ARPA-E program for a subscale demonstration. Soon after that, we will follow up to build partnership with other organizations to form a startup. Here is a slide of our ongoing TCF project where we're going to model test a 1:36 scale system in a wave basin using a hybrid testing to include the effects of turbulent wind from a computer simulation and waves from a model basin. The test will conclude comparing the flexibility features to a non-flexible system. The ARPA-E Atlantis project is called the US Float, which is a SpiderFLOAT design for a 10 megawatt turbine with actuators controlling the arms. The project objective is to lower the cost to 7.5 cents a kilowatt hour or better via control co-design optimization of the complete system. The co-inventors during the LDRD were myself, Rick, and Fabian. Rick and Fabian have moved on. However, Rick is still involved in our ARPA-E effort through Colorado School of Mines. The TCF model test is in progress with a partnership between NREL and Equinor. The ARPA-E effort also is in progress with research partnerships between NREL, Colorado School of Mines, University of Colorado, University of Virginia, and ABS, and with Trident Wind and Equinor as industry advisors. Well, that brings us to the end. Thank you for your attention, and I look forward to the question and answer session.